So this is more TMUA practice. Thank you to Jacqueline and Tyler for writing this. It's about sequences. So we've got geometric sequences, arithmetic sequences, sum to infinities and things. We've also got some iteration and iterative series in here. And finally, also some binomial and trinomial has been thrown in at the end. So just a great paper. I'll link it below. And I'll link Jacqueline's email below as well. She is a tutor, so do hit her up if you need some support. The first question then says we've got an arithmetic sequence with terms these. Of course, arithmetic means the difference between each term is the same. So this minus this must be the same as this minus that. We can just write that as a formula there. And then we can, of course, sort this all out, move it all onto one side, factorize. And we'll end up with m is 3 or m is minus 1. Now, of course, m can't be minus 1 because it says m is a positive constant. So using m equals 3, we can fill in the terms of the sequence. It goes 4, 12, and I don't even care what the next one is, because now I know that the sequence has a difference of 8, and we're looking for the 21st. So I guess we just need to add 20 lots of 8 to this starting term of 4, and we'll find the 21st sequence term is 164. Question 2 then, so sum to infinity is a over 1 minus r. We need to know that because TMUA doesn't have a formula book, of course. So a geometric sequence goes like this, and we have the a over 1 minus r is 3 times as large as its first term, which is a, if you're writing like this. So that's going to be equal to 3a. And the third term itself is 40. The third term, of course, is ar squared. So that's equal to 40. And now we just need to sort out the easiest way of getting a, the first term, out of this. There's a bunch of ways you could do that, but if you notice that a can't be 0, because if a was 0, the sequence would just go 0, 0, 0, which it can't do, because then the third term couldn't be 40. Or, of course, a is 0 here doesn't make this any sense. So let's just divide both sides by a here. We're allowed to do that because a isn't 0. We can solve that for r by cross-multiplying and solving, and then we can put that r back into here, and we'll solve for a without too much trouble. The 4's cancel, and you get 9 times 10 is 90. And we'll have the second question done as well. Another geometric series here, which we'll call this, I guess, goes ar squared, and so on. A over 1 minus r here is 128, so we'll put that down. A second geometric series starts at a and has common ratio 3r, so it goes a times 3r, a times 3r squared, and so on, which I guess simplifies to that. We don't really need to know that, because we can just say a over 1 minus 3r is 384. And again, we're just solving this for a. It's a simultaneous equation. What's the least painful way of solving this for a? Well, I think what I did was I flipped the a over to this side here and just wrote that in terms of r. And then if you times that by 3, you can then shove that result into here, which is what I did, I think. It's not that unpainful. There's probably far easier ways of doing this. But of course, 1 minus 3 is minus 2. Minus makes a plus here. You can, I think, at this point, bring this together, and then this 128 would go on top, right? And then if you divide both sides by 128, because I think that's 3 times 128, you'll eventually get this, and then of course you can cross multiply. People are going to be shouting at me because there are much easier ways of doing this. Quite a nice finishing point though. I never bothered doing 3 times 256, because of course what you can end up doing is just divide 256, which is 2 to the power 8, divided by 2 to the power 3 is 2 to the power 5, and just get 32 without actually having to multiply this, and you get 96 in the end. Just at least a nice little trick there to stop you having to do too much multiplying. We've got an arithmetic progression here. Arithmetic progressions do this. So the second term is a plus d, the third term is a plus 2d, and of course the ninth term will be a plus 8d. And that apparently makes a geometric progression. So what we can say, therefore, is that this over this is the same as this over that, right? Because the common ratio between term 1 and 2 must be the same as 2 and 3. We can rearrange this if we just do some cross multiplying, do a bunch of expanding. Remember, this is a squared plus 4ad plus 4d squared, but the a squareds will cancel with the side over here, so I've already got rid of those. We can divide everything by d here, because if d was 0, then this isn't, well, it is an arithmetic progression, I guess, but it's not a very interesting one, and it wouldn't create a geometric progression with the second, third, and ninth, I don't think. So we can just maybe take out the case d is 0. If it were, then r would be 0, and r is 0 isn't an answer to this, so we can get rid of it for sure. Okay, so we'll get rid of it, and then we can rewrite a in terms of d, which is this. And now I think what we're going to do here is we're going to say, well, if we can replace this d into here, r is of course just this term divided by this term, but now we can put this value for d into here, or the value of a, sorry, into there. All of the d's will cancel, and of course this just equals r, because r is itself the ratio between the two terms in a geometric series. So this one divided by this one, just replace the a's with what you know they are, add these together, cancel all the d's out, 6/5 divided by 1/5 is 6, and we'll end up with our answer as is on the screen. Question 5 is a really great question. It's the only one that I didn't get. I like to do these things under like time conditions, and I just gave up on this question because there were way too many variables for way too few equations. I couldn't find a nice way of doing it. It actually turns out to have a really nice little solution, which I really, really enjoyed. So there's a geometric progression that goes A, B, C. Here's an arithmetic regression that goes A, 2B, 2C. Of course, it must both start at A because the first term is big A for both. So that's fine. And now what we can say is our common ratio R must, of course, be the second term divided by the first or the third term divided by the second. It's the same thing, right? R must be both of those things. We can times kind of cross multiply by here to get B squared equals AC. And over here we can do a similar thing. We must have the same difference between these. So 2B minus A must be the same as C minus 2B, just because it's an arithmetic progression. We can rearrange this for C and then put that C into there and make a quadratic sort of in terms of B and A. Now, why is that helpful? Because it certainly, I got this far and I couldn't work out why that would be helpful and how to get rid of anything else. The reason that it's helpful is a really nice trick. We're being asked for R, the common ratio of the geometric progression, but R is B over A. So what we can do here is we can divide everything here by A squared, and we'll create a quadratic in terms of B over A if we divide everything by A squared. Super nice trick, but of course B over A is itself R, so we actually make a quadratic in terms of R, which we can then solve using completing the square rule formula or whatever you want to do, and we'll end up with our answer of B. Just a lovely question. Question 6 then, we have this is when we start getting these sort of iterative sequences, I guess. P1 is k squared. The next term is k times the previous one. So the next one is just, of course, k times k squared, which is k cubed. And then one after that is k times k cubed, which is k to the 4, and then k to the 5, and then so on. It says what's the product of the first 12 terms? Well, the first 12 terms are k squared times k cubed times k to the 4 times all the way up to k to the 13. The third term is k to the 4, so the 12th term is going to be k to the 13, right? So all we need to do when we times all these things together is add up all the powers. So we're just doing 2 plus 3 plus and so on. You can work this out on your own if you want, or you can just say, well, what is 1 plus 2 plus 3 all the way up to 13? Well, it's 13 times 14 over 2, just using the little triangle formula, and then just take away the 1, because you don't actually have a 1 here. This is 7, 13 times 7 is 91, take away the 1 is 90, and we'll get k to the 90. Question 7 then, again, more iterative processes, I guess, more sequences like this. So we have A0 as a half. The next term is the sum of all the previous terms, is essentially what this says. So the next term is also a half. Then the term after that is a half plus a half, which is 1, and then 1 plus a half, which is 2, and then 2 plus a half, 2 plus 1 plus a half, which is 4. You're always going to get the next term doubled up, because, of course, the only difference between finding this term, which is this plus this plus this plus this, to finding this term, which is this plus this plus this plus this plus this, is just the previous term. So we're just adding the previous term to our collection, essentially. So the next thing is just going to be whatever this was plus itself, so double that, which is 16. And then the next thing will just be 16 plus 16, which is 32. So we're just going to end up with powers of 2. Then it says, find the sum of this, the sum to infinity of 1 over these numbers. So 1 over half is 2, 1 over half is 2, 1 over 1 is 1, and we end up with this sequence when we just do 1 over everything. And now we should recognize, hopefully, this thing here. If you don't recognize this thing here, this is just 2. And if you want to, you can just do a proper a over 1 minus r on it, with r is a half and a is 1. But in any case, you could also just recognize there's some really nice proofs in the world that that's equal to 2. Of course, then we just need to do 2 plus this 2 plus this 2 to give ourselves an answer of 6 in total. This time we're not adding previous terms, but dividing the previous two terms. So x1 is 6, x2 is 3, which means x3 is 3 over 6, which is a half. x4 is a half over 3, that's the previous two terms, which is a sixth. x5 is a sixth over a half, which is a third. x6 is a third over a sixth, which is 2, I believe. Next one would be 2 over a third, which is 6. And what we're really looking for is we're looking for the sequence to repeat, and I think we've now found it, because x7 is 6, x8 is 3. We're back where we started. x9 is just going to be the same as x3 because we're dividing the same two numbers, and so on. So x1 is 6, and so is x7, and so therefore is x13 and x19 and so on. What's the value of x 2023? Well, we know the sequence that goes 1, 7, 13, 19 always equals 6. So that sequence is just the sequence 6 and minus 5. And if we just need to test whether 2023 is in there. If it's not in there, we'll just take the remainder and count up that many. If it isn't in there, then it's just one of the ones that's equal to 6. So we add 5 and we divide by 6 and we find that it is in there. It gives us the 338th term in this sequence. So x 2023 is one of these 6s. Again, if the remainder here had just been remainder 2, you would just count 2 on from the 6, so it would have been a half in that case, but yeah. Cool. Question number 9 then. Sum of the first 2 n terms. Now this is a really cool question, and you get a couple of hints as to how to do it. Firstly, this suspect 2 n terms. Why not just the n terms? But also, a lot of the answers seem to have the sums of things. Because when you look at this sequence, you times by a half, times by a third, times by a half, times by a third. That's not a sequence that we know much about, right? We want a constant thing that we're timesing by. So what we do is we think, okay, 2 n terms. Why would I want 2 n terms? Well, what if you have 2 completely different sequences and you wanted to find the n terms of each of them? That would be 2 n terms in total. And actually, if we break this out into every other term, so 1 and a 6th and a 36th, and the next one, and this one going a half and a 12th and a 72th, you can see that you've got 2 sequences, both with factor a 6th exactly. And so we can find the first n terms of this sequence and the first n terms of that one separately and add them together. So of course, we can use the formula a into 1 minus r to the n over 1 minus r. The r is a 6th here and a is 1. Here it's the same thing, but a is a half for this sequence, still timesing by a 6th. And yeah, we can put these together. I think I was fancy here. I factorized out 1 plus a half because these two things are the same. 1 plus a half is 3 over 2. This is 5/6. 3 over 2 divided by 5/6, you can do a bit of cancelling, I guess. It gives you 18/10 because it essentially is 3 times 6 over 5 times 2. This turns into 9/5, so it ends up being this one, I think, as our answer. Number 10 then, I think this is the last of the sequence ones. Got another sequence defined like this. Let's just play with it a bit. U1, I guess, is just minus 1 to the 2 times 1, just replacing all the ends with 1s. That makes 1. U2 replacing all the ends with 2s is this. U3 replacing all the ends with 3 is that, and so on and so on. Every other term will be negative, of course. So Wn is the sum of all the terms up to n. So Wn is just all of these added together, right, like this, and you just keep going and going and going. And we want the value such that this sequence adds up to 500. Now we just need to stare at this and work out how we're going to add this up. And if what we can do is we can think, well, if we just leave this one alone, minus 2 plus 3 is 1, minus 4 plus 5 is 1, minus 6 plus 7 is 1. We can just say this is 1 plus 1 plus 1. And of course, 500 ones would get us to 500. And how many terms do we need to get us to do that? Well, we need this original 1, and then we need 499 pairs of numbers, all making the other ones. So that's one term here, and then 499 pairs is 998 terms, plus the original 1 makes 999 terms in total, I think. Okay, we have another sequence question to do. I forgot about this one. More dividing to find our next term. We've got x and y, so the next term is x over y. Term after that, will be y over x. Y comes second. Next term after that will be, well, what's it going to be? It's going to be the previous term, which is y over x, over the one before that, which is y, which makes the y's cancel. So this is just 1 over x, I believe. The next term after that will be 1 over x over y over x. The x's cancel, and this leaves, I think, 1 over y. Next time after that will be this one divided by that one, 1 over y over 1 over x. The y goes down here, the x goes on top, so this is x over y. Being good with these tiered fractions is very helpful in lots of cases. Next one is x over y over 1 over y. The y's cancel, and I think this is just x. And then finally x over y, which is going to cause 1 over y, I think. Sorry, x over x minus y, the y goes all the way top, it's going to create y. Now, what's the period of the sequence? Well, we're just counting how long did it take to get back to x, which was the first term. Well, I think it took from 1 to 7, so that's 6 terms in total, so the period of the sequence will be 6. And I should probably have checked by writing down the next term is y. If the next one hadn't have been y, it's not periodic there, is it? It just so happens to match for a bit, and then goes off and does something else, but the next one is y as well. And if the next one's y, then the one after that is definitely y over x, and then it just continues for sure. So it's definitely 6, I think I can say. Oh, I had more sequences. I've completely lost track of how many sequence questions there were here. Good, another thing about period 3 here. So put in A1, and you get A2 is k, lots of 2 plus 2 over 2, which is just 2k. That means A3 is going to be k into 2k plus 2 over 2k. Bunch of stuff cancels here, and you get k plus 1, I think. K can't be 0, because if k was 0, every term would be 0, and then it wouldn't be period 3, it would be period 1, because every term was 0. except for the first, it would just go 2, 0, 0, 0, 0. So k can't be 0, so I can divide by k nicely there and just leave this. The next term will be k into k plus 1 plus 2 over k plus 1, which turns out to be this. And now this is the term for period 3. This is the thing that's going to create, that I want to be equal to the original term. Because period 3 goes this, something else, the same thing again. So we've gone 2, something else, the same thing again. So I want this to be equal to 2 for this to have period 3. Cross multiply, do some solving for k. We get 2 answers for k. Now notice that one of these things is answer C, and then we've also got 2 other answers which are just one of the 2 answers. So okay, we need to actually check which of these 2 work. If you put in k as 1, you get the sequence 2, 2, 2, 2. And that's not period 3, that's period 1 again. Which is, I guess, technically period 3, but not really. So we'll discard k as 1 and just use the answer k as minus 2. And finally, we get to some fun coefficient-y stuff, expanding. We're obviously going to use trinomial expansion. I would highly suggest R2Drew2's video on trinomial and multinomial expansion, because that's all I'm going to use for the rest of this video, because it is so much faster than trying to group up these 2 terms and then do the third one on its own. Coefficient of x squared is either found by doing this by x squared in here, or this by the constant stuff in here. Now look at this, 1 to the power 6 minus 1 to the power 4 means there are no constants in here. So all I need to do is look for the x squared term in all of this, and then times it by 2. Even better, this bracket over here is going to provide no x squared terms, because it's just going to provide constants, x3, x6, and so on. So I just need to look for x squared terms in this bracket here. X squared terms are found by either taking 2 of these and 4 of these and none of those, or by taking 1 of those, none of those, and 5 of those. So our 2 coefficients will look like 6 factorial over 1 factorial, 5 factorial, or 6 factorial over 2 factorial, 4 factorial. Again, watch my trinomial video if you just need a catch up on this. It's super nice and super easy once you get the hang of it. Why is this 18 come along? Well, because not only do I need this coefficient here, but I'm also taking 1 of the x squared, which gives me another 3, so 6 times 3 gives me 18 in total. And here I get 15, but I'm taking 2 of the x's, which gives me a power of 4 from there, so 15 times 4 gives me a total of 60. Add up those 2 options and you get 78. That's how many x squareds are in here, times it by 2 for the final answer, which is 156. I already said that other one has no x's to provide, so can be ignored. Question 14, very similar idea, x squareds here. How do we get x squareds? You can take 1 of those, none of those, and 6 of those. So that's 7 factorial over 1 factorial times 6 factorial. You could also, I guess, do a 0 factorial on the bottom to represent taking none of those, but it doesn't really matter. Or you take 2 of these, none of those, and 5 of those, which is 7 factorial over 2 factorial, 5 factorial. You can work out these factorials super easily, right? This all cancels to make 7, but you're taking an x squared, which involves a 3 term, so times it by 3 for 21. Here you're taking 2 x's, which provide 2 minus 1 terms, which when multiplied by together don't do anything. So that's still going to be 21, add them together, and you get 42 in total. Next one is just regular binomial expansion. There's probably better ways of doing this, but I just expanded this first term to make this, and then said, okay, to get x terms, I either do this times by the x's in here. So that's 1 times 7 choose 1 times a half times 1 to the 6, I guess, which doesn't matter. So this is just 7 choose 1, or 7 factorial over 1 factorial, 6 factorial. Got to be very good at your factorials for this paper. As you can tell, I'm not even going over it because I'm kind of assuming you're very good at them. If you're not, watch my videos on this, or watch anyone else's videos on how to do these choose functions without a calculator very quickly. You are going to have to do it. The next one is going to be, you can times this by x squared terms to get x terms. So it would be 4 times whatever x squared terms we can make here, which is 7 choose 2 times a half squared times 1 to the 5, which again doesn't matter. So this is 7 choose 2. This all cancels to be 7 times 6 over 2 is 7 times 3, which is 21. This 4 cancels with this 4, so that's nice. So this is just going to be 21. And then lastly, you can do this times x 3 terms, which are going to be 7 choose 3, so that's 7 factorial over 3 factorial, 4 factorial, times this cubed, times 1 to the 4, which doesn't matter. This is going to be an 8th, which cancels that to make a half. This is cancels to 7 times 6 times 5. That's a 6 anyway, so this is 7 times 5 divided by this 2 that's left over here. So we get all these numbers, add them together. Notice that if you add these 2 together first, you get 42 over 2, which is 21, and then this 21 gives you a 42 in total. And the very last one, a very similar question to this got asked in last year's math paper. Just a gorgeous trick. Break this 1 plus x to the power 6 out into 1 plus x to the power 5 times 1 plus x, because now we can group these 2 brackets together all to the power 5 multiply them together, difference of two squares makes it go away. And now we can ask a very similar question to what we did in 14, which is how do we make x to the 5 times out of these two brackets? Well, you can either do 1 times x to the 5s from here, or x times x to the 4s from here. This is not going to provide you with any x to the 5s because this is an even power. So all we're looking for is x, or 1, times x to the 4s from here. How do we get x to the 4s? Well, it's just 2 of those. So it's 5 choose 2 times minus 1 squared, I guess, is not going to matter, times 1 to the power 3 is also not going to matter. This cancels to 5 times 4, divided by 2 is 5 times 2, which is 10. And so times by the 1 here is still just 10, and the answer is 10. Thank you so much for watching, and thank you for Jacqueline again for writing some such good questions.